Limits number 7 is all about limit properties. And this tells you what you're allowed and not allowed to do with limits. And down here we've got a list of properties right here. So the scalar multiple property says if you're doing the limit and you're multiplying by a constant right here, it's okay just to pull that constant to the outside. And the next one, the sum and difference one, says if you do the limit of a sum or a difference, that's the same as finding each limit separately and then adding them together. And the product rule says that if you're doing the limit of a product, it is the product of the two limits. Ditto for the quotient. So all of these are basically intuitive. So if you have a quotient, you can do the limit of the numerator divided by the limit of the denominator, provided you don't get a 0 in that denominator. The limit as x approaches c of a constant is just that constant. And the composite one is a little bit tricky here. So the limit as x approaches c of f of g of x is f of the limit as x approaches c of this inner function right here. So you do the limit as we approach c of g of x and then find f of that. And there are some restrictions down here in this note. If f is not continuous at that limiting value, so if f is not continuous at whatever answer you get in here, then we cannot use this property. Or if that limit does not exist, we can't use this property. And we're going to learn how to do some workaround so that we can still find an answer, even if we're not using this property exactly as it's stated right here. Some of these examples we're going to look at are pretty straightforward and basic, and some get a little bit tricky. So let's just start with this first one. And I am given two limit values. So the limit as x approaches 3 of f of x is -5, and the limit as x approaches 3 of g of x is 8. So I know these two limit values, and I'm asked in example 1 to find the limit as x approaches 3 of x times f of x. So I'm going to use the product property that says the limit of a product is the product of the limits. And that gives me this statement here. And now I can evaluate each one of these limits separately. This first one will just be a direct substitution to evaluate. And for the second part, I know the limit as x approaches 3 of f of x is given right here as being -5. And the product of -5 and 3 is just going to be -15, and that is my answer to the first example. Go ahead and try example 2 here. It's going to be a combination of the sum and difference property along with the scalar multiple property. So my first step is to split this into two limits across this subtraction sign. And then my next move is going to be to take this 4 and pull it to the outside. And I also went ahead and evaluated the limit as x approaches 3 of g of x. I have that value up here as being 8. And now all I have to do is look up this limit, and I know that is that -5 that I had before. And when I calculate that, I get a final answer of -28. Example 3 is similar. I will just be pulling the limit values from a graph instead of being told what those values are. So this will go back to limits number 1. So let's go ahead and apply that sum and difference property to number 3. So the sum will just be split up into the limit as x approaches -1 of f plus the limit as x approaches -1 of g. And I can see from the graph as I approach x equals -1 on the graph of f, I'm heading for a y value of 1. So this value here is a 1. And if I approach -1 on the graph of g, I can see as I approach from either side, I'm heading for a y value of 5. So the answer to that part is a 5. And when I add them together, I get 6. And that is the answer to the limit. So question 4 is a little bit different, because if I look at this and I say as x approaches 1 of f, and you look here, and because I'm approaching two different y values, I would say that limit does not exist, because as I approach from the left, I'm hitting 3, and from the right, I'm hitting 1. And that also applies as I approach 1 on the graph of g. From the left, I'm approaching a different value as I am from the right. So you might be asking, how do you add does not exist plus does not exist? And you might be tempted to think the answer to this would be does not exist. However, and I wrote this off to the side here, this is a general limit, and it will exist if the left and the right-hand limits are equal in value. So what I actually have to do here is find the limit from the left and the limit from the right. So the limit is x approaches 1 from the left of f is 3. So this part here is going to be a 3, plus the limit is x approaches 1 from the left of g is a 1. So that's 3 plus 1. So my limit from the left side is going to be 4. And now I'm going to do the same from the right. So here's my right-hand limit. So as x approaches 1 from the right side on the graph of f, I can see I'm heading for a y value of 1. So this is a 1 plus. And as x approaches 1 from the right on the graph of g, I'm heading for that y value of 3. So that's a 3. And 1 plus 3 is 4. And what I see is I actually have the same left and right-hand limits. And if your left and your right-hand limits match, that means the answer to the limit question is that answer. So my answer here is actually 4. Questions 5 and 6 are a practice of that quotient rule. So on question number 5, I'm asked to find the limit as x approaches 2 of f divided by g. So I'm going to apply the quotient rule first. So I find the limit of the numerator and the limit of the denominator, and I can see in my graph that as x approaches 2, whether I'm on the graph of f or whether I'm on the graph of g, both of those limits exist, so I'm in business with this one. It looks like on f, my limiting value is 1. And on g, it is also 1. So this just becomes 1 divided by 1. So my final answer here is just 1. If I try to do in number 6 what I did in number 5, and just do the limit of the numerator and denominator separately, what I find is as I approach 1 of f of x, because I'm heading toward 2 different y values, I'm heading for a 4 from the left and a 3 from the right, that limit does not exist. So if you get a does not exist limit, what I would say is go ahead and try the one-sided limits. So if I just look from the left of this quotient right here, so as x approaches 1 from the left of the graph of f, I get an answer of 4, so that's 4, divided by, and as I approach 1 on the graph of g, I am approaching a y value of 1, so that's 4 divided by 1, and that gives me an answer here of 4. So now I need to check out the right-hand limit. So now here's my right-hand limit. So as I approach from the right side on the graph of f, my y value is a 3. So this is a 3 in the numerator. And on the graph of g, as I approach the x value of 1 from the right, I get a y value of 1. So this is 3 over 1, or 3. So now on this one, from the left and from the right, I have 2 different values, which means my general limit, the question on number 6, because I have 2 different values, the overall answer is does not exist. Question number 7 is going to use the product rule for limits. So as x approaches -3 of g and of f, so here's -3 on each one of these graphs. And if you just try to apply that property, it's going to say the limit as x approaches -3 of g of x. When you look here, that limit does not exist because I'm approaching 2 different y values. So what I'm going to have to do is consider the left and the right-hand limits for question number 7. The limit as x approaches -3 from the left on the graph of g is 1. So it's 1 times, and as I approach -3 on the graph of f, I'm hitting 0. So this is 1 times 0, which is just 0. And now I need to consider my right-hand limit. So now x is going to be approaching -3 from the right. And when I look at the graph of g of x, as I approach -3 from the right side, I have a y value of -1. So this is a -1 times. And if I look at approaching -3 from the right side on f, as I get closer to -3, I'm approaching a y value of 0. So this is 0. The product is 0. And what I see is I actually get the same left-hand limit and right-hand limit. And if these equal, then that becomes the answer to the general limit. So my answer here is 0. The last three examples deal with the composite rule. And just a refresher, it's on the front, but I'll write it next to the problems right here. So what the composite rule is telling me is that if I'm doing the limit of a composite function, f of g of x, I do the limit as x approaches c of the inner function and then evaluate f at that limiting value. So for question number 8, my inner function is actually the f and my outer function is the g. So the letters have flip-flopped from how that original rule was given. But I first need to find the limit as x approaches 2 of the inner function, which in this case is f. And I can see from my graph over here is I approach an x value of 2 on the graph of f. My y's are approaching -1. So my first answer over here is going to be -1. And then I just do g of -1. And at -1, and this isn't a limit, this is a function value at -1. G has a value of 5, so my final answer here is 5. This question was pretty straightforward because the limit as x approaches 2 of f existed, and also g of -1 was defined. If those two things don't happen, they get a little bit tricky, and that's what I'm going to look at for questions 9 and 10. I'm actually going to start and do number 10 first. So the first thing I need to do with this composite function is do the limit as x approaches -3 of f of x. Evaluating this limit isn't the tricky part, so the function is not continuous, but I don't need it to be. As I approach x equals -3, whether it's from the left or from the right, I'm approaching a y value of 1, so this limit has a value of 1. And now I have to evaluate g of 1. And here's where the trickiness comes in, because if you look on function g, at 1, I'm not continuous. And a requirement to use this property was g had to be continuous at this value right here. So what that means is I can't use that property. But here's going to be our workaround. Because as I was approaching x equals -3, I'm approaching that y value of 1 from above 1. So I'm approaching 1 from numbers greater than 1. Which means to evaluate this limit, I'm going to approach 1 on the graph of g from numbers greater than 1. So from the right side, and as I approach 1 from the right side of g, I can see I'm headed for a y value of 3. So the answer to this composite limit question is 3. Now the reason that this worked is because of what was going on right here. I was approaching this 1 from above from both sides. So whether I tracked from the left or from the right, I am approaching this y value of 1 from numbers greater than 1. So I knew when I came over here, I was going to approach this 1 from numbers greater than 1. And I tell you that because when we get to number 9, it's going to be a little bit different. So I'm going to start the same. I see a composite function. So I'm going to do the limit as x approaches 3 of f of x is the first thing I do. And I look over here on the graph of f, and I can see as x approaches 3, that limit exists and its value is 1. So I've made it past the first part of this. And now I have to go and do g of 1. But then when I go and I look at the graph of g, just like in question number 10, g is not continuous at x equals 1, which means I cannot use that property. So I'm going to try to use the workaround that I did in number 10. The difference on this one is, if you look, as I approach that y value of 1 on the graph of f, I am coming from above on one side and from below on the other side. Notice how that was different from what happened in number 10. In number 10, as I approached that -3, I was approaching that y value of 1 from above on both sides. On this one, I'm approaching from below and I'm approaching from above, which means our workaround is not going to work. That theorem that we had above, that property is not going to work, which means this answer is a does not exist. So a final word on the properties of limits. They're pretty straightforward for some of the problems, but they get a little bit more difficult for others. Just some of the things that we looked at. If you have a limit that does not exist, try doing the left-hand limit and the right-hand limit and see if you get matching values, and that's a workaround on that. Or when you're dealing with these composite functions, when you do this initial limit right here, if you're approaching that value from the same direction, in this case from above, if you're approaching that y value from the same direction, which is above, then when you evaluate, just approach that value on the other graph from that same direction. And if you're approaching that value from two different directions, from below and above, then that's when you go for a DNE as your answer. It's a little bit tricky. It's going to take a little bit of practice for this. I did a limits assignment that was on paper because Delta Math didn't quite cover this well enough for you. But just do the best you can do and we'll practice.